everyone, so in this lecture we're going to talk about Cartesian products, which is another way to build a set given some old sets. So similar to how we have seen before, you can construct new sets from old. This will be a brand new type of set. In order to get to what the definition of a Cartesian product is, first I just have to quickly explain what an ordered n-tuple is. So an ordered n-tuple, you can write it like this. You use sort of these parentheses, and you can write A1, A2 up to AN, and each of these AIs here are elements of some sets, right? They actually could be from completely different types of sets, and I'll show you that in just a minute, but really they can be any objects you want. But the important thing is that they have an order to them, so you can't mix these up, and I'll show you in just a second. But an ordered n-tuple will look like this, and it's an ordered collection where each of these AIs is, you call that the ith element, and I ranges from 1 to n here. Now you've encountered ordered n-tuples probably in a previous class before. For example, when you learned about the Cartesian plane, like R2, and you're plotting points, those are ordered 2 tuples, or you would just say an ordered pair, right? And just one thing to note is that 2 ordered n-tuples, they're only going to be the same if they're the same in every single one of the coordinates, and they have to be equal in each of those positions. So for example, if you look here in this example 1, I have an ordered 3 tuple, and it just goes 1, 2, 3, and you know the 1, 2, and 3, those are the objects, but that's the specific order that we want. So for example, another ordered 3 tuple could be this one right here, 2, 1, 3. And we would say that these are not equal to each other because they have to be equal in every single position. So the first position, you see that they're not equal in the like the first element. The second element, they're also not equal. In the third element, they actually are equal. The 3 is equal to 3, but they have to be equal in every single one of those positions for them to actually be equal as an ordered n-tuple. Now this is different from a set, because remember, with a set, order is insignificant. So for example, I could have a set that contains the elements 1, 2, and 3. And if I were to reorder these in any way, and remember, when you write a set in rostered form, you use this sort of squiggle bracket here. But when we're talking about ordered n-tuple, we're going to use left and right parentheses. Okay, so the set containing the elements 1, 2, and 3, I could write that in 6 different ways, but they're all the same set. So for example, if I wrote it like this, 2, 1, 3, as a set, I only care about the objects within it. So I still have the same objects as I do in this set, right? 1, 2, and 3. I still have 1, 2, and 3 in this collection. Same thing here. I still have 1, 2, and 3, and so on. So with a set, when you write it in roster form like this, the order is insignificant. But with an n-tuple, that is very important because it's part of the definition. It's an ordered collection. Okay? Okay, now that we understand ordered n-tuples, we can actually use those to create new types of sets. Okay, and one way to do this is you can create the Cartesian product of 2 sets. So if you give me 2 sets, A and B, I can take their Cartesian product, and you'll write it like this. It looks like I'm writing A and then your old version of your times operator, B. And so this would be the Cartesian product of A and B. And writing this in set builder notation, it's saying that you're going to give me pairs of elements that look like this, little a, little b. These are ordered pairs, right? And little a has to belong to this first set A, and the second element has to belong to the second set B. Okay, so just you're going to have these ordered pairs, and the first entry will be in A, and the second entry will be in B. So let's look at a specific example. Let's say that I give you the set A, which has the elements 1, 2, and 3, and I give you the set B, which contains the elements 1 and 5. So let's give the Cartesian product of A times B and the Cartesian product of B times A. Okay, so to construct A times B, the Cartesian product of A and B here, All right, the definition says you're going to create these pairs. First element has to be in A, second element has to be in B. So looking at these two, I could have the first element is a 1, right, because it's an element of A, and then the second coordinate could be a 1 or a 5. So I could have this ordered pair, or I could have this ordered pair where the first entry is a 1, right? Similarly, I could start with a 2, right, and then I could have 1 as my second coordinate, or 5 as my second coordinate. Or I could have 3 as my first coordinate, and then 1 and 5 as my second coordinate. Okay, so these are all the possibilities that I have. So every single one of these is an ordered pair where the first entry is in A and the second entry is in B. So this would be the Cartesian product of A and B, specifically in this order, so A times B. And B times A, let's see what that would look like. Well, same idea, it's just that the first entry has to be in B, second entry has to be in A. So I can have a 1 in the first coordinate, and then I could have a 1, 2, or 3 in the second coordinate. So I'd have 1, 1, 1, 2, or I could have 1, 3. And if I had 5 as my first entry, I could have 1, 2, or 3 as the second entry. So I have 5, 1, 5, 2, 5, 3. Okay. And if you look at these two sets, this example actually shows you that these two Cartesian products are, in general, not going to be the same, right? Because if you just look at these two examples, look at the whole collection. They're not the same set, right? I do have some elements that are in common, like 1, 1 is in both. But I have 1, 5 in the first one, and I do not have a 1, 5 down here. I do have a 5, 1, though, right? So these two, in general, will not be the same sets. Okay, well, what about this example here? So let's say that the first element, or the first set, sorry, is the empty set, and the second set is the set of real numbers. Okay, so what would the Cartesian product be? Well, the Cartesian product, by definition, I have to pick elements from the first set as my first entry and elements from the second set as my second entry. Well, just looking at this definition, right, I'm going to, you know what, let me just back up. So this will be empty set, Cartesian product with R, right? So by definition, this will be the collection A and B, where A is in the first set, this empty set, and the second entry is in the second set, the set of real numbers. So do you see a problem with this? Well, if I'm requiring to build pairs, right, ordered pairs, where the first entry is in the empty set, there is no such element, right? No such elements, right? So what does that mean? That means that you're not going to actually be able to give me any pair, right? You will not be able to give me something in the first coordinate, which means that no pair will actually exist, right? So this list would actually be empty, right? No ordered pairs. Okay. Well, if your list is empty, well, then this is the empty set. Okay. Well, that's kind of interesting. It looks like if you take the empty set and you Cartesian product it with the reals, you actually get the empty set back, which is kind of strange. That's quite different from the previous example, right? If I took the Cartesian product of the A and B, they don't even look like the original sets, right? These are pairs, whereas the original ones were numbers in each set. Okay. So it's a little bit strange, but that's actually what the definition leads to. You can expect similarly, well, if I do B Cartesian product with A, same problem is going to arise, right? Because now I'm going to be looking for ordered pairs again, but A will now be a real number, and B will be an element of the empty set. But again, there's no such element. So if I can't find a B, there's no way I can find an ordered pair. So the list of ordered pairs, there would be none, right? So there would be no ordered pairs. Okay, so continuing on, in general, I could take the Cartesian product of any collection of sets, and that would look like this. So if I had n sets, I could do a Cartesian product with a1 times a2 times ... all the way up to an. Probably should have another little times there. And what this would look like is an ordered n tuple. Okay, in the ordered n tuple, you're going to have each of these AIs be an element of the set big AI, right? So what this is telling you is that the first entry has to belong to this first set, second entry has to belong to the second set, and so on, all the way up to the last entry, an, has to belong to this set, big An. Okay, and this is for all I from 1 up to n. Okay, so you're going to get a collection of n tuples like this. All right, so just to illustrate this, let's look at the this example here. Okay, so I have the sets A, B, and C, and I want to find the Cartesian product of A times B times C. So let's just look at what that would look like. So by definition, A times B times C, Cartesian product here, I'm just going to list out triples. These will be ordered triples, where the first element has to belong to A, second element in B, and third element in C. So let's kind of go systematically. So I could have 1 as my first entry, 1 is my second entry, and then for the third entry, now that I'm at set C, I could have X, Y, or Z. So I could have X here, I could have 1, 1, Y, I could have 1, 1, Z, okay? And then I could also have 1, 5, right? I could have 1 as the first entry, 5 as the second entry, and then I could have X, Y, or Z as the third entry. So I have X, Y, okay, so let's say that we want to find the Cartesian product of A, B, and C. Then we're going to end up with ordered triples, where the first element will be in A, second element will be in B, and third element will be in C. So for the first element, I could use a 1 because that's in A. I could use a 1 since that's in B. And then now for the third entry, I can use X, Y, or Z. So I could have 1, 1, X, I could have 1, 1, Y, I could have 1, 1, Z. And that takes care of the 3 where I do have a 1 and a 1. I could also have a 1, 5, and then I could have X, Y, and Z. So 1, 5, Y, 1, 5, Z. Okay, and then now I've exhausted all the possibilities where I have 1 as the first entry, right? And now if I go to 2, I could have 2 in the first entry and then kind of repeat these, right? So I could have 1 in the second entry, and I could have X, Y, or Z in the third entry. So I could have 2, 1, X, 2, 1, Y, 2, 1, Z. And then I could have 2 as the first entry, and then I could have 5 as the second entry. So I have 2, 5X, 2, 5Y, and 2, 5, whoops, 2, 5Y, and then 2, 5Z. And I believe we've exhausted all our possibilities here. So again, it'll be these ordered triples, right? First entry is in A, second entry is in B, third entry is in C. All right, so for the next example, let's say that you want to find the Cartesian product of C and the union of A and B. So maybe it might be a good idea to first actually calculate what is the union of A and B. So the union, remember, will just be, it's sort of concatenating these two and then taking out repeats. So I have 1 and 2 in there, and then I also would add in anything I haven't already added in, right? So B already has 1, so then I would add in 5. Okay, so again, the union, right, just combine these collections together, right, to give you the union, but you might have to take out repeats. Okay, so I have 1, 2, and 5. So now if I want to calculate the Cartesian product of C and this union, now I have to pick, so what are these going to be? Well, I have 2 sets here, right? I have C and I have this union. So I'm actually going to have pairs of elements, right? I'll have first entry is in C, second entry is in this set, the union. So first entry is in C, so I could have X as the first entry, and then the second entry I could have 1, 2, or 5, right? So I could have X1, I could have X2, and I could have X5, all right? And then first entry could have been a Y instead of an X. So if I use Y as my first entry, second entry can again be 1, 2, or 5. So I have Y1, Y2, or I have Y5, and I could have Z as my first entry, or I could have, and then I could have 1, 2, or 5 as the second. So I could have Z1, Z2, and Z3. 5. All right, and now I've exhausted all my possibilities here. Okay, so a good question might actually be, well, how big is the Cartesian product actually going to be? What is the cardinality of that set? How large will that be? Well, it's actually not too difficult to calculate this. The cardinality of the Cartesian product for finite sets, so if these A1, A2, and up to AN, those sets are finite, then the cardinality of the Cartesian product will actually just be the product of the individual cardinalities of each set. Okay, so if you kind of look at our examples here, right? So example up above, right? So just a quick little mini example, right? Up above, this is example 4.1, right? So 4.1, so 4.1, the size of A Cartesian product B Cartesian product C should be the size of A times the size of B times the size of C, the cardinalities of each one individually. So what was the cardinality of A, B, and C? So cardinality A was 2, cardinality, because there's 2 objects in here, right? B had cardinality 2, there's 2 elements in this set, and this had 3. So it would be 2 times 2 times 3. So what is that? 12, right? So 12. And we can also see this above. Okay, what do I mean by that? Well, we just calculated it using this theorem, okay, but you can also see it up above. There's actually 12 elements up here. Now, why is this theorem true? So if you kind of think about this, why did I end up with 12 elements? Well, we sort of had this systematic procedure, right? How many choices do you have for this first entry, the first entry of this triple, right? I have one of 2 possibilities. Okay. Second entry, I have 2 possibilities, and the third entry, I have 3 possibilities, and each of those choices are all independent of one another. And usually, when you have these independent choices, you would end up multiplying them to get the total, right? So that's why I have 2 choices for the first entry times 2 choices for the second entry times 3 choices for the third entry, and I'll have all 12 of these possibilities. So it matches our work up above, right? In example 4.2, so 4.2, what's the cardinality of, I think it was C Cartesian product, this union. Okay, well that would be the cardinality of C times the cardinality of this union. Okay, well the cardinality of C was 3. In this union, we had 3 elements in that set. So I should end up with 9. And you can also see this from up above, right? That we actually had 9 total elements in this set, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements in that Cartesian product. And again, you can think about that mathematically by just saying, okay, how many choices do I have for that first entry? I have 3 choices. I could be an X, a Y, or a Z in that first entry. Second entry could be one of 3 choices, right? So, and they're independent, so I'll end up with 3 times 3 total ordered pairs. Okay. All right, and that's pretty much what we just need from the Cartesian product construction. So in general, you really have seen this before, perhaps in a previous class, right? You're used to, do you remember graphing functions or plotting points? Do you remember the Cartesian product of reals and reals? This would be like you have an x, y, such that x is a real and y is a real, right? And usually visualize this as, the Cartesian, we called this the Cartesian plane, okay? And you have these points, x and y, right, on your x and your y axes here, right? So you're actually kind of familiar with this from before, and these were ordered pairs, right? So for example, 0, 1 was different from 1, 0, and you plotted those points when you were learning this in your algebra classes or your pre-calculus classes and so on. Okay, but now we're looking at it in a much more general context. It doesn't have to be real number. It could be much more general. Okay, and 5.6 gives you sort of a summary of the chapter. This was 5.4. We're going to just skip 5.5. If we have time at the end, we might do that.